last problem, it's not really a problem so much, not going to solve for anything with the number, but we are going to set up an equation. So this last problem is number 5. A spacecraft, all right, is positioned between the Earth and the Moon so that the gravitational forces on the spacecraft exerted by the Moon and the Earth and the Moon cancel. So what that means is, remember here we have the Earth, and the Moon's out here somewhere. It'd be farther away than that, but it'd be off the board, so I can't show it. So where would a spot be that would be such that a person kind of floating in between the two would be pulled equally by both? Would that be down here near the Earth? No, come on, you know that. Would it be right down here next to the Moon? No, but it's going to be closer to the Moon. Well, why? Because the Moon has less gravity. So in order to make up for the fact that the Moon has less gravity than the Earth, you got to be closer to the Moon than the Earth. So I'm just going to put an X somewhere out here. Maybe it's like here. And at this point, the Moon pulls on the person and the Earth pulls on the person. And let's go ahead and see what happens. What would be my equation to solve for where that would be? How would I do it? Actually, we just answered part A. It says, is the position closer to the Moon, closer to the Earth, or halfway in between? Explain. Well, it's closer to the Moon because the Moon has less gravity, so less mass. Less mass means less gravity in the equation for gravity, which we'll put up here, Fg equals, well, we need big G. Clean that up, big G. M1, M2 over R squared. So this equation kind of keeps coming back at us too. Universal gravitation. So this shows that mass is very important when it comes to gravitational pull. But so is distance. Distance is even more important because it's squared. So for the Moon to make up for the fact that it has less mass, you can do that by pulling hard if you're closer to it than you are to the Earth. So there's the answer for A. Okay, now, how would I actually solve that? What would I do to figure out where that is? Well, what we'll do is we'll set it up. I don't know where my eraser went. Be right back. I'm back. Okay. The question says, where would the gravity be the same? If it's going to be the same, that means the gravity from the Moon and the gravity from the Earth are identical. So that would mean that the force of gravity from the Earth is equal to the force of gravity from the Moon. Let's substitute in. Force of gravity equals that. Equals that. That means I'm going to have this equation on both sides. So let's go ahead and write that in. Big G, mass. Well, what mass? Well, this is the Earth, so we're going to need the mass of the Earth. And what about the other mass? Well, that's the mass of the person. That's the mass of the person floating in between. So we'll put down mass Y for, not for my mass of you. You. You're floating in between the Moon and the Earth. Divided by the distance R to the, actually the distance to the Earth. That would be the center of the Earth, not the surface, the center of the Earth. Remember, those distances were calculated to the center. Equals, all right, the force of pull from the Moon. So a big G, the mass of the Moon. This is you. You're in between the Moon. That's you. And the radius of the Moon, or the distance to the center of the Moon, squared. My. Oh, check it out. Speaking of my, things cancel. Gravity's gone. Well, gravitational constant's gone. You are gone. You don't matter. You're irrelevant. You don't matter. You don't even matter. No, you don't. No, you... Sorry. A little over the top. Sorry. Yes, you do. You're important. So, but in this problem, you're not. So your mass is gone. It doesn't matter anywhere. It's who's up there in between the two. It's going to be in the same spot. No matter what we put up there. Now, let's go ahead and clean this up and solve for the distance. Actually, I forgot what I was solving for. Part B. So I'm the distance from the Earth. Okay, so you want to know how far away you're going to be from the Earth. So let's go ahead and solve that. I'm going to go ahead and finish solving that up here. I'm going to take this, and now we have it cleaned up. We'll have the mass of the Earth over the distance to the center of the Earth squared, mass of the Moon over the distance center of the Moon squared. Solving for the distance to the center of the Earth, cross multiply, divide, bring that up, switch it with this, switch those, bring this over here. What do we look like? Mass of the Earth multiplied by r mass of the Moon, the mass of the distance of the Moon, mass of the distance of the Moon, the distance to the Moon, distance of the Moon's center squared. We brought that down and switched those. So that's over the mass of the Moon. There's the mass of the Moon, not that. Equals the distance to the center of the Earth squared. But wait, for only $19.99, you also get, of course, you have to call now. Operators are standing by. It's an infomercial. One more step. Let's get rid of the radical. You radical. How do you get rid of a radical? Throw them in jail. Okay, square root both sides. I take square root of both sides. That goes away. Boom, got this. Now we have the distance to the center of the Earth. This will be the center of the Earth. So actually, if you want to know the distance to the surface of the Earth, you can calculate what r is and then subtract the radius of the Earth, the actual radius of the Earth, and you'll know how far off the surface of the Earth you would have to be all pulled in both directions equally and just stuck in place. All right, so that's how you would solve it. There you go. Have fun with that. Okay, we're all done.